I have the pleasure to introduce the keynote speaker of this morning. Before the Ida P. Rolf Foundation created the independently run Fascia Research Society, its board voted on who they wanted to have as a keynote speaker for this next Fascia Congress. Mark Driscoll was one of the selections. Thereafter, he was voted as the first president of the Fascia Research Society, and thus he was asked to maintain his presentation, which he accepted despite all other Congress planning and board responsibilities that he took on. This speaks to the strong support of our fascia community. It is also nice to have an engineer on our side. Mark is a professor of mechanical engineering here at McGill University. He recently co-authored a new fascia book with me and others and has published many papers speaking to the biomechanical importance of fascia. He runs 2 laboratories at McGill and is consistently innovating with many patents and products to his name that help people with disability. To that point, he holds the Canadian Research Chair for Interdisciplinary Innovation of Medical Technologies. It is my pleasure to thus invite Mark to give his talk entitled Fascia, the Unsung Hero of Spine Biomechanics.
Thank you, Robert, for that introduction, and to you, Patricia, for that warm summary of all the great things that Tom did for this community. Alors, bon matin, bienvenue à Montréal. Good morning to all, and welcome to my beautiful hometown of Montreal, which is also home to, as Robert said, McGill University. So McGill, as you can see here in the different pictures, are the various campuses downtown. And McGill houses 40,000 students, 10,000 of which are actually graduate students. So it's a very research-intensive institution, and I consider myself very lucky to be working there and to be working with these brilliant graduate students. They always impress me. I have maybe 10 or so students from the lab here at this event, and if you see that they're from McGill, harass them with all the questions you can have. I told them it's a great conference to come to. I'm convinced you'll be as impressed as I am. So how does a geek, and I consider myself a geek, I know it, I'm an engineer, I love numbers, how does a geek like myself become obsessed with the spine? And bear with me, there's a little bit of a backstory, but it'll make sense from where I come from and how I align my actual research, and it actually all ties in to McGill. About 3 weeks ago, like many, I was kind of grappling on to the last days of my summer vacation before the start of the semester. And I was at my cottage with my wife and kids, who are young, and my kids were asking, hey, Dad, what are you going to talk about at the event? So I said, Dad's going to talk about how the back works. And my son said, cool, he's stuffing marshmallows in his face. And my daughters kind of laughed, and they said, yeah, sure thing, Dad. And they laughed, one, because as an engineer, they think I work on a calculator all day, which is half true. And 2, because as long as they've been alive, and my eldest daughter is 11, they've always known me to struggle also with back pain, like so many people, right? So like many researchers, I'm very motivated and driven in my field. And the way it all circles back to my time at McGill, and this audience will appreciate this, and that's quite some time ago. So while I was an undergraduate student at McGill, I was playing hockey. And if you're not from Canada, everyone plays hockey in Canada. We don't have a choice, or at least I didn't. And long story short, hockey is kind of like rugby on skates, and I was pushed into the boards, blew up my ankle, and then all my problems started, from ankle to knee to hip, all the way up to the back. The leg I've more or less figured out, I think. We'll find out on the run tomorrow. The back is a continuous struggle. And because of that, I'm super excited to be here. A number of clinicians in the audience. We have Stuart McGill, who I think is amazing in back research, and so many others. So Don't be surprised if I take the opportunity to try and corner you and get some personal advice. So that makes me a researcher and a patient, and I'm constantly reminded by my own struggles and my kids that I need to do more and know more. I think collectively as an audience, given the widespread prevalence of this issue, I think we need to do more, or at least share our ideas together. So what do I hope to offer you? As an engineer, my lens or perspective with which I view the back is a little bit different. In a sense, I view it from a mechanistic point of view. I also, because I work with numbers, restrict the research mainly to objective interpretations. And like we saw in the video this morning, I'm well aware in studying something as complex as the back that this has its limitations. I know that, trust me. The way I get around it is I make super smart friends that are smarter than me, like Dr. Schleip and many of you who I'm sure know what I'm talking about, where I can call upon you and see if what I'm talking about from the numbers perspective actually holds any clinical relevance. So, what have I found thus far? I look mainly at the back from the disability perspective, although I'm pretty certain the conclusions I'm going to share with you today extend very well into performance, which is also interesting. To date, I've actually developed medical devices that go in patients to help and correct deformities, and in the last 4 to 5 years, I've turned my focus more to the early onset, try and understand back pain from the biomechanical perspective, with the aspirations of kind of develop new diagnostic methods, or hopefully, like I said, share this information with you as clinicians. So, what are the 2 main findings that I've done? I always start my presentations in giving away the ending and starting with the conclusion. It gives me the impression that during my talk, I have to convince you of what I conclude rather than just laying it on you at the end. The first conclusion I hope to impart on you is that local passive mechanical properties impacts internal load sharing in the spine. And don't worry, I'm going to unpack it a little bit more. The second conclusion is that the thoracolumbar fascia, muscle pressure, not tension, we all know tension is important, but muscle pressure, as well as intra-abdominal pressure, influences spine stability. So, how did I come to these conclusions? Like many, I employ an in vivo experimental platform. This would be, your average living human, animal studies. We also, in the laboratories, do ex vivo studies. So this would be cadaveric studies, studies on excised spines. We have some really nice robotic spines that you can push and do whatever you'd like to. They don't complain. We have analog functional spinal segments that we can hook up to mechanical testers. All of these are great and very relevant research platforms. The one I'm going to emphasize today that I hope to expose this audience to is called an in silico platform. So think about this platform as if you take a digital twin of myself, put it off to the side, and then as a researcher, it's great because you can conduct all the crazy experiments to this digital twin that you want to. You don't have to worry about ethics. You don't have to worry about widespread populations ruining your statistics. And like I said, for an engineer, it's great because it's number-based. Now, even though you may be unfamiliar with this platform, pretty much everyone in this room has already placed a lot of confidence into this experimental platform. If you flew here, drove here, or are sleeping in this or another hotel, I can assure you that this in silico platform has been used in a critical design step in designing those planes, cars, and buildings. Why? Because engineers have long employed these methods in aerospace, automotive, and civil engineering. I would say in the last 20 years, this has made its leeway into biomechanics, and probably within the last 10 years has really been leveraged. And it's a very powerful platform, but powerful if used carefully. So, Let's get started and jump into that first conclusion that hopefully I'm going to convince you of. And once more, that's local passive mechanical properties impact load sharing in the spine. I'm just going to repeat it over and over to convince you. So how did I find this out? This is a concept that I was very fond of probably about 10 years ago and revisited recently. So yes, only engineers are fond of mathematical theorems, and it's the concept of stress shielding. If you're unfamiliar with this concept, stress shielding refers to how if you put two things next to each other, one being more rigid than the other, the rigid structure is going to shield the less rigid structure. This is well accepted in the field of orthopedics. You could clearly see that occurring here with this total hip arthroplasty in a timestamp from A to C, where because the implant is more rigid than the surrounded bone, it shields it, and the bone starts to resorb and disappear, which of course causes problems of fixation. The analogy I love to use was if I were to take a brick and a sponge and I put them on a stage and I actually stand on it, the brick is going to support all my load while the sponge will be shielded by the brick. If the sponge had a personality and some legs, they would get up and walk away because it would feel rather useless, similar to how the bone is walking away in image C. Now, some time ago, I showed this to have an influence in spine disorders such as scoliosis here, where in scoliosis, on the concavity of your spine, the tissues actually get stronger. The bone gets stronger, the intervertebral discs degenerate and hence get more rigid locally when compared to the convexity. Now, there's no implant here, right? But my question was, can this asymmetry in mechanical properties create that shielding effect? Ran some assessments, and yes, it can. And next, can it play a role in the pathomechanism or progression of this disorder? And we showed it to have an influence. A really interesting thing, at least I think, is if we were to take this patient, put them in a corset that beautifully and fully realigns the spine, which I know is impossible, but say the corset successfully realigns the spine, this patient still has this asymmetry in tissue properties, you're still going to get a load allocation bias. The stiffer side will still get more loads than the less stiff side, okay? So, fast forward 10 years, I wasn't kidding when I said I was self-motivated. I've gone to see all kinds of therapists. Everyone's poking me and stretching my back. They say, Mark, you know, you're too tight, you have lower cross syndrome. And then I started reading, I was like, yeah, you know, I feel a little bit tight. And then I started to think, you know, why is nobody looking into the concept of stress shielding and tension, especially in light of what everyone here knows, the very important interconnectivity of our body, right? If I take an elastic and I stretch it, great, I stretch the elastic. If I put a steel wire between there and I try and stretch it, the wire is going to be the thing that resists me, and the elastic is not going to feel any tension, okay? So the question is, can this concept of stress shielding apply in tension, and is it going to tell me anything about my back? So there we jump into our in silico platform, right? We can take a patient, any patient with MRI or CT, build an accurate 3D reconstruction of that patient, include the tissues that interest us, and then run simulations on. So here we focused on the lumbar spine, selectively included some tissues. The next thing, which is really cool, it's as easy as kind of copy-paste. We have our digital twin, we make a clone of that digital twin, and then we're mean to the clone. We give the clone low back pain, and how we do that is we actually include mechanical properties that are known to occur in patients with low back pain. More specifically, what we did here, we increased the moduli or stiffness of select muscles, reduced the cross-section of those muscles, and increased the thickness of the thoracolumbar fascia. Now, before we progress and run any kind of actual assessment, we have to undergo a lot of validation, which means, okay, we build this model, this digital twin, we make the clone. Our plan is to impart flexion and load the model. So we have to make sure that the data that it's feeding back to us actually makes sense. So a lot of steps that I'm skipping over are actually in the process of building, validating, making sure it's a robust model, non-sensitive to some of the hypotheses or assumptions that we're actually making. So the model's built, the clone of the model is built, and now we're ready to fire off and run our analysis. For further clarity about how, again, I know I'm biased, I'm an engineer, how great I think this platform is, if you were trying to execute this study clinically, you would have to have two identical twins walk into your office who have done the exact same activity they've done their entire life. Strangely convince them to let you selectively dissect some of their tissue, send them to my lab, we're going to test them, stretch them, get the mechanical properties. I don't know how, but you go back in, you stitch up the tissue, all the while loading them with all the sensors you could actually possibly think of, right? So ethics would never fly. You'd probably get arrested, and not a feasible actual experiment. But we can actually do this on these actual platforms, which I think is great. So circle back and to shine further clarity on what we were planning to do, right? So this is, can local stiffness in passive soft tissue in one's back actually cause or give any tendency of load allocation bias or the notion of stress shielding? In short, the answer is yes. More specifically, if you look at what's happening, you're getting more load going to the actual muscles and soft tissue. Not much, but a decent amount. And even more interesting, if you look at the thoracolumbar fascia, which remember just had an increase in thickness, there was about 15% more stresses going into that thoracolumbar fascia. Now remember, the only difference between this digital twin and the clone that we get back pain are these small changes in mechanical properties and thickness. Of course, the model is in pure flexion. Later on, we integrate muscle activity into the model, but nevertheless, I'm convinced these conclusions will still hold. Okay, so what does this mean for me? It's fine, it's tight. It doesn't really give me any guidelines about my own back. I'm a bit more tight on the right side than the left side. So back to the drawing board, can the presence of unilateral asymmetries create the same effect? So that's what we did. We deleted our low back pain digital twin, copy-pasted, created a new clone, and we gave this one unilateral low back pain. So the right side underwent all those changes, which once more, short increase of the modulus of the muscle, reduced in their cross-section, and increase of the thoracolumbar fascia. Just on the right side, nothing on the left side. For further clarity, what this actually equates once more, based on the analogy earlier, we have the steel wire on the right side and the elastic on the left side, which is kind of my situation. So once more question, can the presence of a unilateral asymmetry lead to this stress shielding effect? Can we quantify it? Once more, the short answer is yes, and we're pleased to see this. Once more, if we look more specifically at what is going on, again, here we couple all the soft tissues together. Decent amount of more stress going into those soft tissues, and if we look at the thoracolumbar fascia, also upwards of 15% more stress in, again, the right side of the low back pain or unilateral low back pain patient. I think for this audience, it's interesting on two fronts. First, it's important to acknowledge that these simulations, yes, they're virtual patients, but they are validated. They undergo the same transition or movement, right? So they're both undergoing identical flexion, I mean to the 0.0000 millimeter, right? The only distinction are these asymmetries of property and mild increase in thickness that we're doing. So, if you as a clinician have a patient that comes in that otherwise shows no signs of offset geometry, which I guess you would consider compensation, if these underlying biases exist in a patient, you're still going to have an irregular transition of loading within the body. And of course, in the long term, this could lead kind of to a degenerative cycle and could cause problems. So something to look out for. On the flip side, if you have a patient like me, has all kinds of compensations, favors, standing on the right leg, etc., you teach them to kind of go about their business and be this kind of symmetrical drone, which is very difficult to do. But you don't address any of these soft tissue asymmetries once more. Even if you've corrected their patterns, these underlying asymmetries exist, you're still going to have a load allocation bias within their system. And I think that is rather important. Another way to say this and summarize this, again, back to these conclusions, would be that local passive mechanical properties impact load sharing in the spine. And if you take that sentence in Google Translate and go from geek to English, it would say something like passive tissue health matters, right? And once more, given the interconnectivity of our body, I think this is a very important conclusion that is thrilling for me to share with this audience. I've been secretly watching facial expressions as I talk. It's something I do. So I'm talking about conclusion one. I've seen no kind of disgruntled shaking. Nobody's tossing tomatoes at me. So you either had a really good time last night, like I did, you're too polite to kind of show your disagreement, or you're somewhat convinced with the conclusion. So thank you for all those, but I'll take the latter and convince myself that I've convinced you of this first conclusion. So now we're going to jump to the second conclusion. Thoracolumbar fascia, muscle pressure, abdominal pressure influences spine stability. So why did I start to look into this very busy and very complex area? Like I said, I was constantly seeking consult with different clinicians, and I was receiving conflicting information, right? So they're poking me, having me do tests. They're like, Mark, you know, you're too much core, too little core, overdeveloped paraspinals, underdeveloped paraspinals, and I started to obviously get confused. And because I have an obsessive personality, it drives my wife and it drives me crazy, I dove into this rabbit hole of literature. And there's a lot of great stuff out there, notably by a number of you in the audience. And in reading this literature, where I thought I can contribute as an engineer is in employing these in silico platforms, which are less common in this field, to see if I could corroborate some of the findings that were out there and what I could possibly add, if I could add my own twists or flavor to these interpretations. So this is what I did. We go back to our digital twin here. Here it's getting larger. We take a slice through, I don't know why I'm doing a slice like this. We slice them through L3 and kind of transversely-ish because it's somewhat inclined. And this is the cross-section that we get here. We selectively choose the tissues of interest. Here we have the posterior middle thoracolumbar fascia as well as the intra-abdominal region. We code in the material properties, again, based on literature, and then we start to pull things in that interest us. For this study, what interests us were the pressures in what I'm going to call the paraspinal chamber, the pressure in the intra-abdominal region, and then we could fluctuate these and do whatever we'd like. This is simply a video of one of the 1,000 simulations that we performed. It doesn't necessarily deform like this, it's just visualization. So, we create this digital twin, we slice them to somewhat of a two-dimensional piece, we add these pressures, and now we want to look at what are the loads being allocated through those soft tissues. The first thing we found was you get some decent forces that are actually conveyed through the thoracolumbar fascia, whether at the spinous process or the lateral raft onto the sides to the transverse processes of the vertebral bodies. Now, another really smart friend of mine, Dr. Andrew Vliming, did such an experiment on the bench side where they had pneumatic chambers. We got similar forces to what they got, which is great. What I wanted to add, or highlight rather, what that I think is incredibly undervalued, are the importance of the direction of those force vectors, right? So even though the magnitudes may be considered low, lying between 2 and 20 newtons, depending on how high we jack up the pressure in our digital twin. Like I said, they're transverse or transverse-ish based on this cut, right? And if you compare that vector to the rather wimpy moment arms of our paraspinal muscles and their wimpy tendons that I learned, by the way, I think these are important. So I think they can play an important role in adding to the stability of the spine by way of pressure conveyed through the thoracolumbar fascia. The next thing we did for this model, because again, we could do whatever we want, we jacked up the pressure in the abdominal chamber. We don't have to worry about the patient exploding. And we were curious, what was going to happen to the actual force vectors, whether it be the direction or the magnitudes, which I just shared. Interestingly enough, there appears to be this balance, and when the pressure goes over a certain point, the forces will reduce at the posterior end, so the spinous process, and they would actually grow at the lateral raphe. I'm not saying one is better than the other. Of course, it's function dependent, and we'll talk about that in a little bit. What I think is very interesting, though, is there appears to be this synergistic balance between balancing pressure in your intra-abdominal region and your paraspinal, because it'll clearly adjust how the loads are allocated through the soft tissue that we included, which again here is the thoracolumbar fascia. So I could already anticipate my anatomists friends calling me when we publish this and screaming, we're not two-dimensional, what are you doing, it's nonsense, and I get that, right? Although I think the conclusions would still hold, so in anticipation of that call and for a number of reasons, we kind of beefed up our model a little bit, right? So now it's from the sacrum to L3, more of a volumetric assessment. We once more include the mechanical properties, validate it for function, pressure in the abdominal region, pressure in the paraspinal chambers, and we rerun assessments. For this paper, we looked at different lifting patterns. We wanted to compare these famous squat versus stooped or kind of kyphotic, lazy gardening type of lifting. And to do that, what happens when you actually do a stooped lift, the pressure in your abdomen drops considerably compared to squatting. The pressure in your paraspinals increases twofold compared to squatting based on in vivo studies. So we integrated those pressures in our model and we said, okay, what happens? The first thing that happens, not surprisingly, the pressure or stress in your intervertebral disc goes up. So that's no surprise. If you have disc problems, kind of don't do lazy stooped lifting. And the next thing that happened, conversely to what we explored before, is now the tensional force at the spinous process was increasing, right? So once more, I'm not trying to say one is better than another or you should have pressure in this region over the other. What I'm trying to say is there really appears to be this interesting, like I said, synergistic or not, but there's a balance between how these pressures in these regions will actually convey forces through your thoracolumbar fascia as we simulated. Okay, so what did this mean for me? Again, engineer, always going to different clinicians. Not much, right? I started to obsessively poke around my belly and my back, trying to figure things out. I was even more confused, and then I took a step back and I was looking at the modeling and I said, okay, I'm still confident with the conclusions we're putting forth, but I wanted to beef up, so to speak, and integrate more accuracy into this model. The first thing we looked at were muscles, right? And a lot of engineers and people in biomechanics model muscles as pure force vectors, which is okay for many interpretations, but for me, when I was looking into pressures or trying to allude to the importance of pressures, I needed to have a volumetric representation of muscles. Not only did I need a volumetric representation, but it had to behave physiologically. There's this very interesting linear correlation between the pressure developed in your muscles and the actual force conveyed at the ends, at the tendons. And you can see that here in the chart. So I challenged one of my brilliant students, as mentioned earlier, to develop a physiological muscle that would convey tension. So here it's just a representation, but the muscle will contract, convey tension at its extremities, develop that pressure within the epimysium and other layers. And then I said, okay, well, you got to validate it. So we compared it to studies that used the tibialis anterior, correlated pressure to muscle force output. Here's a graph where we overlay our simulation data to the actual in vivo data, all to say that the muscle is working well, right? It's tensioning. We can control the force we want to apply, and it will develop an actual pressure similar to our muscles do, which is great, or at least I thought was great. Next, we turned our attention to the intra-abdominal cavity. Challenge the student. Okay, we're trying to develop a full thoracolumbar model. We have to model the intra-abdominal cavity. So they look into the literature, pull the actual moduli or elasticity of this cavity. Once more, looked at in vivo trials that correlated volume to pressure, where you could derive bulk modulus or compliance, which is more of a clinical term, ease at which the abdomen will expand. And the annoying from a math perspective part about the abdomen is you can actually kind of control the actual stiffness of your abdomen, right, just by engaging your core. So we did a parallel study where we looked at the actual elasticity, which is analogous to contracting your core. We looked at things like what is the thickness of the abdomen, what if you have a larger abdomen or smaller abdomen, all the while trying to validate and build this model, like I said, that would behave physiological. Over here again, we have our simulation data overlapped with clinical data, all to say that the intra-abdominal volume now in our model develops pressure and behaves as it otherwise should. So now we're starting to get excited. Now we're at the point where our model has 273 soft tissues. Again, it's not everything, right? But it's what we are interested in looking at. So 273 soft tissues and extensively validated, right? Because recall, these models are only powerful if you've taken the time to make sure that they behave appropriately. What we've done, we validated them for disc pressures, for movement, so we can kind of push the model, squeeze it, and the actual data points that we're going to get make sense contrasting to those in vivo and other ex vivo platforms. It's also validated, at least in my mind, to the point where you can actually use this to develop medical devices, which I said in a past life I used to do. And similar to how it's used for planes, cars, and buildings, now companies are using these platforms to develop and optimize medical devices. And you can actually leverage this simulation platform to approve your device, whether it be CE mark in Europe, FDA in US, Health Canada in Canada. And I know this because I'm on the committees, and like I said, I used to do it in a past life. And I've circled now my interests to try and understand what is actually going on, even though there's less money. But it's more interesting, and less money for research funding, but it's more interesting for me. So now we have this larger model, more tissues. We're starting to model, pressure more accurately. What did we do? And I'm going to dwell on this study a little bit because I think it would interest this audience. So again, create a digital twin. Here I'm just showing a focus on the lumbar spine. We impart 350 newtons of flexion, which is about 35 kilograms of mass. So if I was going over time and my friend Robert charges me and shoves me, I don't see him coming, I'm going to bend forward. And that is what essentially we're doing in this model, right? You don't tell it, you perturb it with a certain amount of force, and you see how much displacement would actually occur. From the engineering static equilibrium perspective, if we're able to reestablish that initial position, it gives us an idea of stability. So let me unpack this a little bit. On the y-axis, we have the displacement, so how much movement occurred when Robert shoved me. And we have different vertebral levels from L1 to L5. If the histogram is higher, there's more displacement. If it's lower, it doesn't move at all. Or if it was 0, it wouldn't move at all. Now, like I said, we could turn things on and off within this actual numerical model. So we're going to use the baseline as I'm solely this excised spine. Dr. Steckel ran up, dissected me. I just left my spine. Robert shoves me, and I bend forward pretty far, as you can see. Next, we include muscles, but only passive muscles. They don't fire, they don't expand. What happens, I go a bit less far. Still a decent amount of travel, but a bit less far. Next, what if we have active muscle? Okay. Rather expectantly, if my muscles fire and are active, well then I'm going to go less far. Next, strip away the muscles, just leave me with my thoracolumbar fascia, and this one, rather impressively, I'm able to actually go less far than before. Lastly, strip away the TLF, give me an abdominal region, let me contract it and build intra-abdominal pressure. I still travel, but it gives you an idea of the decent amount of ability to the IEP, which I fully agree with as kind of a clinical measure. You know, you brace, your spine definitely gets more stable, I can assure you that. So these are individual contributions we tried to dissect and look at. What if we include some of those together? What actually happens? So, same baseline, just the XI spine, no tissue, lots of travel. Now, what if I have thoracolumbar fascia and active muscles? Remember, they contract, they build pressure. Impressively, not that much travel. Next, active muscle, IEP, less travel, pretty impressive. Next, IEP, TLF, also less travel. And finally, everything that we've simulated, active muscles, TLF, IEP, of course, that's the best one. That'll hold me erect as much as possible up here as I get pushed forward, okay? What's interesting here is it's never the concept of superposition, right? It's not like A plus B is AB. If you subtract one and add the other, it doesn't give you a clear indication, which is expected, right? It's a very complex system going on. I also think this data also affirms or supports the notion of these pressures. And I just want to dwell one more minute and look into this further. This is the result of all the tissues firing, IEP, TLF, active muscles. And on the far right, we were able to get 93%. Again, engineering static stability, right? Close second, as combining things, was the TLF and active muscle. Third, not too far away, was IEP and TLF. And the best performer from the passive and individual perspective was the thoracolumbar fascia. Now, I'm not necessarily saying that one of these is better than the other. Of course, it depends on your purpose or your goal, right? And we're going to get into that shortly. What I do think, and I'm going to repeat it once more, I think it asserts or supports rather the importance of pressure and of all these soft tissues, notably thoracolumbar fascia, in maintaining or contributing towards spinal stability, which again is the conclusion too I'm trying to convince you of. Okay, so which of these is optimal? Well, from the engineering perspective, optimization is a bit different. And so this would be activation strategies, I guess, for you. Typically, there's 3 commonly accepted activation strategies. So this would define how inherently, without thinking about it, my mind's telling, you know, which muscle to fire, which to relax on a constant basis, right? The concept that is most commonly accepted is one that defines efficiency. Right, so I'm walking around the stage probably to be efficient, or I'm lazy, so I'm bouncing around on different soft tissues, and I don't want to stand up here and get tired, right? So that's happening right now without me thinking about it or kind of dictating what's going on. The next one would be one that defines stability at all cost, right? So I'm going over time, Robert charges me, I can't run away, I clench up to not get pushed over, and that would be a scenario which is stability at all costs, right? It's not one that makes sense in the long term because I'd be standing up here sweating and probably shaking after a bit. Another commonly accepted activation strategy would be one that would locally reduce stresses, such as if you have a herniated disc, you could adopt strategies both geometrically and muscles firing without knowing it, all the while to locally reduce the amount of pressure or compression on that particular disc. So these are 3 that are commonly floated in the literature, which of course makes sense and I agree with, right? For me, I wanted to look into, can there be an activation strategy that is pressure-based, right? Based on everything that I've learned thus far about IEP and muscle pressure, right? So can there be a strategy that either functions towards maximizing pressure or actually reducing that pressure? And this is what we did. To achieve that, we coded in different systems into our digital twin. So that's, think of like thousands of lines of codes. We're basically giving a brain to our digital twin, coding in those activation strategies I just defined. So we have the 3 that are accepted, and now we have one that is to minimize muscle pressure or maximize muscle pressure. We then run an optimization based on the cost functions we want to optimize. So it's a Pareto optimization system. And what that means, for example, if my goal is to reduce muscle activity and be as efficient as possible, all the while not, of course, falling over and kind of standing somewhat straight, I hope, while I'm presenting, it would find that local point, right? It would run thousands and thousands of different simulations and then give me the optimal point where I'm straight-ish as possible while using as much or less amount of force as possible. And that's what we did. Here's the results of the efficiency goal, and I'll guide you towards the points I want to make rather quickly. So first, this is an example of all the scattered points we get. The one it punches out as having minimal displacement and reduced muscle loads are there. And then we could look at anything we want, right? We don't have to pipe the patient with sensors. We just look and zoom in and take out the interpretations we want. We looked at muscle force, intramuscular pressure, thoracolumbar fascia, resistive forces, and lastly, intervertebral disc compressive forces. So this is for that commonly accepted efficient goal. If we can compare what the stability goal gives us, not surprisingly, muscle force goes up, muscle pressure goes up. Remember, I'm clinching. If we're trying to reduce low disc pressure, pressures in the disc go down, as does muscle force. So this, no surprise. I mean, for us, it was super exciting because it says, our coded brain is actually working, but there's no surprise here, nothing groundbreaking in these conclusions. If then we look at how it performed when we had a low pressure muscle as the goal. What's happening? No surprise, muscle pressure goes down, as does muscle forces. Last one, high muscle pressure. Awesome. Muscle pressure goes up. So does the actual forces or resistive forces in the thoracolumbar fascia. Now again, I'm not saying one is better than the other. I'm not saying I'm walking around this stage purely basing myself on a pressure-based activation strategy. I think it's most likely conceivable that there's lots of different activation strategies being selected at any time. I was super pumped and pleased to see that, hey, one potentially based on pressure holds its own in a sense that it's converging to a solution that is upright and that makes sense as far as the amount of forces and stresses involved, okay? So all that to say, to circle back to conclusion 2, which I've convinced you of, and that is thoracolumbar fascia, muscle pressure, intra-abdominal pressure influences spine stability. Okay, so I have about 5 minutes left, and I'm going to take you through now, kind of give you some insight into what we're doing in the laboratory. Remember, we're engineers. We don't have your awesome palpation skills or your clinical insight. So when I was going around to different, clinics and seeking different consults, they would say, hey, you're too tight here. And I'd always kind of poke myself and be like, how are you figuring that out? So I wanted to develop a tool that would allow me as an engineer to actually quantify these notions. Not just for myself, but also because, don't forget, there's different platforms we employ, right? We have the robotic ex vivo model where we could use cadavers. And some of my students are currently doing these parallel tissue testing to verify this concept of stress shielding. I have no doubt they will. In moving into in vivo trials, like I said, I would love to fill, humans with all the sensors in the world, but it's not actually possible, right? So I wanted to come up with a non-invasive or practical method to actually quantify these tissues in the hope of corroborating what I've shared with you thus far that we discovered on this simulation platform. So years ago, and this is to show you the progression, this tool was no good. So years ago, we'd kind of had this makeshift kind of force sensor that we'd compress below the abdomen of select patients. Here was patients with cerebral palsy, so it's a severe musculoskeletal disorder. who can't sit independently on their own, right? So they underwent 2 years, 100 patients, heavy physical therapy. All the while, every 6 months, we would poke them below the navel to try and measure or allude to intra-abdominal pressure. So you have the results, both progressed. But in writing this paper, I wanted to say we're measuring intra-abdominal pressure, but I couldn't. We just weren't. We were just alluding to it. Okay, so it's not giving me the tissue properties or the IP that I necessarily want. Then again, I'm going from clinic to clinic, and people are saying, hey, they're probing me with dry needling and acupuncture, and which was fine. I enjoyed it, but I said I had this not so great idea, but I thought was great at the time. I said, okay, what if I put kind of a force sensor in the clinician's hand, and while they're poking through my tissues, I could derive or extract the mechanical properties. So all the while we were doing a project for Johnson & Johnson, we had a bunch of cadavers. So we ran this test on a cadaver where we inserted a probe through these tissues. We got a force displacement profile shown here. We can compute things like creep, et cetera, everything we wanted, because again, it's a cadaver. And now, as geeky engineers, we're like, okay, we're going to reverse engineer the mechanical properties. So we build this numerical model, try and superimpose our predicted mechanical properties versus those measured in clinic. Did a great job. I bring it to my clinician friends. They're like, you're crazy. No acupuncturist is going to, dry needler is going to actually hold this in their hand while poking your tissues. So I said, okay. Published a paper, but scrapped it as far as an idea to use long term. So now what we're currently developing, still in development, is this product that you can put on your abdominal cavity or a muscle. You create a negative pressure, it creates a hemispherical deformation of that underlying tissue from which you can directly compute, not infer to, but compute the underlying pressure and the elasticity of the tissue that you're deforming. So fairly bold claims, and of course we have to actually validate it, which we're trying to do in the lab. The first study that we did, we took a whole bunch of cadavers. I think we had 12 fresh cadavers. And the gold standard for measuring intra-abdominal pressure is through a urinary catheter. So obviously, you're not going to get many volunteers to actually do this study. The poor graduate student who did this study, I'm still impressed by her. But anyway, she would get called in the morning by Dr. Vienne, who assisted Dr. Stecco with the anatomy lab dissection. She would have to show up and put in a urinary catheter, and then I shouldn't say we, it was all her. She'd move the cadaver in certain positions. We'd get a direct measurement of intra-abdominal pressure, put our device on, extract it, and try and corroborate the data. So decent amount of accuracy, at least for us. Next, there are other devices out there that measure tissue stiffness, such as the Endento Pro, which I really like, and others you might recognize. We used calf muscles of living people this time, took quantification of tissue stiffness and the one that alludes to elasticity, computed ours, compared them, and we were happy enough, okay? So this is a work in progress, but of course, in our lab, the whole point is to develop and leverage this to corroborate or support some of the information we found thus far with our famous digital twin and digital twin with low back pain. Okay, so let's take a step back and summarize what we've discussed thus far. We focused a lot on the disability spectrum. We were looking at trying to find indices or new notions that contribute to spine biomechanics, all the while alluding to low back pain, which there's other causative factors, of course, but as an engineer, these are my only tools that I could use. Hopefully I convinced you of the first conclusion, right? And again, this is maybe stress shielding can occur in tension. It's very important what those passive properties are, and they can definitely impact the patient, whether they're geometrically flawless, no compensation, or not. If there's a bias there, they can create an issue. What we're going to do is hopefully measure it and corroborate that in vivo. Next, thoracolumbar fascia, muscle pressure, intra-abdominal pressure definitely influences spine stability. I don't think there's a debate there. I'm happy to discuss it. And again, we're planning to measure that in our way in our trials. And for me, it was very thrilling to share our research thus far with this, well-respected clinical audience, so I'm very happy to that. For me personally, my journey as a researcher and a patient, and hopefully one day a decent hockey player again, is going to continue, and I look forward to that. Okay? So in closing, 2 more slides, bear with me. So we're ahead of time though. So first one, of course, as everybody knows, the students are the one behind the scene. I opened in saying they're brilliant graduate students at McGill. My lab's the same. Again, please harass them with your questions. You will be impressed, I assure you. So a huge shout out and thank you to the team that I have the pleasure of working with. We always have to acknowledge our sponsors, so a big thank you to the sponsors, and most importantly, un grand merci à vous. Thank you very much for your attention. It was my pleasure. Yeah, we can have a few.
So thank you very much also for being in time, so I didn't need to do the experiment to push you forward. I would like to do the opposite, where I pull you backwards with 35 newtons in a backwards direction. So this means we have time for questions from the audience. Anybody willing to stand up? Do we have a runaround mic, or we have somebody with a loud voice?
I try a loud voice. Is that sufficient?
Yep.
So the question is, for the modeling and the abdominal pressure, it's very important to see the hip position. If you see the hip position, because that determines your angles on the right side, I'm missing the oblique muscles and the rotator abdominis. Is there a reason why they pushes out? Or can you elaborate a little bit in that direction?
Yeah. So the question was, and thank you for that, was, of course, the hip position will influence, the orientation of the lumbar spine, as well as which soft tissues are involved or not in that position. Yes, of course, this model, I said we had 273 tissues involved. There's much more than that, I assure you. When it comes time to making assumptions, because to give you an idea, when we ran that optimization simulation, I said we code it in the brain and we push enter and get results, but the computer overheats for 2 days and it takes forever, right? So we have to make assumptions and make it simplistic enough that we can make interpretations. So there are many assumptions, like the one you said. Yes, we didn't look into the hip position, which I think would play a role. This is definitely something we can do. So we haven't looked at that. When it comes to other assumptions that we've thought of, or my friends have told me, like, okay, well, how come you chose this mechanical property versus that mechanical property, right? We can perform sensitivity analyses, which means we can simulate the full range of spectrum of properties that are relevant, all the while keeping an eye on what the model's spitting out and what is our end conclusion, okay? If our assumption offsets or disrupts our conclusion, we have no confidence in the conclusion and it's not robust, right? So there are many assumptions. We've thought of a lot of them, but we didn't consider that one, and that's something we could definitely look into in the future. So thank you.
May I have a question?
Yeah.
Because we had Serge Grakowecki at the very first Fascia Congress, and he had done some mathematical calculations 20 years ago, how important the thoracolumbar fascia would be for spinal stability. Then Stuart McGill, who we have now as a keynote speaker, thanks to your invitation, did some improved mathematical calculation and showed no, Grakowecki was wrong based on his improved calculations, and the thoracolumbar fascia is not very much important. Now Mark Driscoll comes and tells us, yes, it is. So at the next conference, do we have somebody else? Or
Yeah, so the great thing about researchers is, we're always wrong, and if you're convinced you're right, you're in the wrong field of practice. So, yes, I was aware of Serge's study as well as all the great work by Stuart. I was telling him yesterday that, and you could ask my grad students, when they show up in the lab, the first thing I do is I give them, Dr. McGill's book, and I said, read all this, and then we could start. I think, like I said, when I was looking at the importance of the TLF, I think what was undervalued was the orientation of that force vector. Serge was more referring to the TLF in pure tension, so in this direction. and not the orientation of the force vector. As far as the studies by Dr. McGill, a lot of great ones. Actually, a lot of the data points that we pulled in our assessments were based on the work done in his laboratory. So, cautious, polite researcher, nobody's wrong, but or nobody's right, but we're all wrong. But I do look forward to seeing Dr. McGill's talk.
Yes, I have a question. I know you're interested in the thoracic abdominal area. Your future research, are you going to be looking at the upper part and the neck and the cervical area as well?
Yes.
And its influence on the whole spinal and abdominal area?
So excellent question, and it kind of piggybacks a little bit on the first one, you know, go lower, and you're saying go higher. Yes, of course. It takes time, so I'm not using this as an excuse, I'm explaining our perspective. It takes a lot of time to develop these, and there's a lot of models out there that I think are great, but may not have been as exhaustively validated. I think as within our group, it's something I stress a lot in my students to the point that they roll their eyes when I start harassing them on validation. And so because of that, it's taken time. So I've been at this within McGill for 5 years, or just over 5 years now. So our plan is definitely to extend it above and beyond, and I look forward to the insights of what you offered as well as the other gentlemen. So thanks.
So you say that it offers more stability. Is it possible that it actually creates more rigidity?
I'm sorry.
So when you said that abdominal pressure, thoracolumbar fascia, right, and muscle tension will increase stability, correct?
Yeah.
But is it possible that it's actually an interpretation? Could it be that it offers more rigidity? So is it a positive or a negative?
Is it possible that the pretension offer?
Is it possible that all of those structures together are actually creating more rigidity versus more stability?
I mean, yeah, it's possible. I think rigidity and stability go hand in hand depending on how you define it. Our approach was from a static equilibrium or engineering perspective. Rigidity may not be a good thing. It really depends. Another thing I'd throw back at you, and so when I go see clinical consult, everyone's saying, you know, too stiff, too rigid, right? Of equal importance that could equally cause stress shielding is if something is too weak as well. So of course it's function dependent, patient dependent. I'm saying globally as a whole, if you're lacking spine stability, the tissues as well as the pressures that we highlighted definitely contribute from the static equilibrium perspective. Not saying it's a good thing.
Yeah, question about the abdominal pressure and the muscle activation. Now, when you did the experiment, was the muscle activated in a continuous manner when you noticed the pressure increase, or is, because the muscle, you know, you have concentric, eccentric contraction, right? So when you made the conclusion that increasing the muscle activation increases the abdominal pressure, what exactly do you mean by that?
Yeah, so I'll answer. If I don't fully answer, it's because I didn't entirely hear, but you're asking about how we modeled the actual presence of muscle contraction in the intra-abdominal region, correct?
Correct.
So we don't, as of now, still work in progress, we don't actually have all the abdominal muscles, obliques, transverse, and rectus abdominis. We don't have them. We could simulate the presence or contraction or not by changing the actual elasticity of that abdominal chamber that we've done. So that's how we emulate the presence of these muscles for the time being. So if the elasticity of the abdominal chamber goes up, which would be getting more rigid as if you were bracing, of course the contribution to spine stability as we defined it goes up. There's two reasons why that would go up. One is because it assists in conveying those important, or what I'm considering important forces in the thoracolumbar fascia. Of course, they expand between your diaphragm and pelvic floor very well. That's well known. But another thing that they actually do, which I also think is undervalued, is the concept of buttressing. So it's like an architectural term, is if you put two rigid things next to something that could move, it's going to lend stability to that. So here you have your intra-abdominal chamber, which essentially is filled with an incompressible fluid, right? So if you don't allow the volume to expand, your bulk modulus, or which is kind of stiffness, goes through the roof, kind of to infinity. So you have that in the front, you have these pressurized paraspinals in the back, and that creates this buttressing effect too. So we don't directly simulate them, we change the moduli, but we think it's accurate enough at this time, at this iteration of the model, to simulate the presence of abdominal muscles.
So if you translate that to for example, a person, a live person, that means you're asking that person to contract their abdominal core? Is that what they're doing?
Yeah. In the model, we go through a range. So we have a very low elasticity, which would be you're not contracting, versus a high elasticity, which would allude to you are contracting. I don't ask anyone to do anything. I'm an engineer. But we're saying that the higher elasticity, analogous to contracting your abdominal core, will increase spine stability, is what we're saying.
Okay, so here's another question. So with the muscles that are, if you're asking a person to contract their core muscle, right? Because, you know, this is, I think this is applicable for runners, right? They can be, because if they're just concentrating on training their core muscle, they can't, during their run, they cannot just contract their core all the time. They cannot be thinking about the muscle activation, right? So that means the pressure will change. But the role of fascia play into this, I think, is very interesting and worth exploring, is that the property of fascia sometimes when you activate the fascial connection to the core through the glutes, the core can be automatically activated. So.
Okay, that's good insight. I didn't consider that. Thank you.
Thank you.
Maybe one last question.
Hello.
Hi.
Thank you so much. It's an amazing presentation. My question is, having delved into all this research and have done all the computation, did you learn anything as a patient of lumbar spine? And what are the practical, basically, pearls, let's say, that you've learned from your research, perhaps maybe in positioning or posturing or even using your breath to improve, you know, to increase your intra-abdominal pressure? And have you been able to implement it, and did that affect your back pain?
So thank you for the question and concern. So, I mean, yeah, I learned a bunch of clinically for myself. I'm constantly doing a lot of stretching. The breathing, I haven't looked into, of course. I'm careful to the point of borderline obsessive about kind of balancing how I allocate my weight distribution in my motions. But it's an ongoing process. And so I'm not a clinical expert, I'm a number expert, but I appreciate your question and concern. Thank you.
So thank you very much. For me, this is a historic contribution because of the decade-long debate. We're starting with Grakovetsky and others, and Bokluk and Stuart McGill, and this is now really moving out on a much more reliable level. And luckily for us, you showed, if I understood it correct, compared with intra-abdominal pressure, compared with active muscle contraction, the stability of the thoracolumbar fascia is the single most important contributor to that. So this is, for me, a historic contribution.